So, before moving to the computer, just let us look at this figure in greater detail. So, what we have is basically the same picture as in the last page, and here this is basically the lattice is drawn, and what we shall do while we write the code is that the temperature along these boundaries, they are essentially fixed, right. And so, we are not going to update those points. Instead, what we are going to update are this lattice point, this lattice point, this lattice point, basically whatever is there between this blue line. So, we are going to update the temperature at these at the points within this blue line, because at the boundaries here and here and here and here, basically they are fixed, the temperatures are fixed, they are boundary conditions, they are not going to be updated, the temperature are going to remain fixed because they are boundary conditions. What will change are the temperature in these points, right, in the middle of the plate, and that will evolve with iterations. So, while iterating, the loop shall go from this point, and basically from this point to this point to this point to this point, and not over the entire lattice, right. And we are basically have a 34 cross 34 lattice. So, the loop shall essentially go from 2 to 33, right, or L x minus 1, again 2 to L y minus 1, and so on. And now, to look at the code, so the code is called vi Laplace dot f90, because we are solving a Laplacian essentially with the appropriate boundary conditions, right, and the program is named Laplace implicit none. As you know, Lx I have set to be 34, Ly to be 34, that is a square lattice. We are going to update the temperature and store the temperature in a new array. So, we are going to store the temperature in this lattice 1 comma Lx and 1 comma Ly, and after an update I am going to store the value of this temperature into the old temperature, and using the old temperature we are going to calculate new value of temperature over the entire lattice in the iteration, right. So, that is why we have two arrays. These are dummy variables I, j, jj, kk, and so on so forth. Now, here basically I am giving the boundary temperature, the increment in temperature that I shall give along the boundaries, basically 0.1, right. And so, what I am doing, I have defined the values of dx and dy, though we shall not be using them, because basically the expressions becomes independent of dx and dy, but if you had chosen finite values of dx and dy, or dx and dy was different, then you would have to use the more complicated expression which I had shown earlier, right. So, here I am specifying the boundary conditions, and from 1 to Ly, that is along the y direction, for each points in the y direction, and this loop is over 1 to Ly. So, for x equal to 1, right, that is the left side of the square, where x equal to 1, for different values of y, I am saying that the temperature is going to increase from bound temperature. Bound temperature has been set to 0, and the increment of temperature is 0.1. So, as you increase j along y direction at different points along the boundaries, you are going to have essentially 0, 0.1, 0.2, 0.3, 0.4 up till the top at basically 1 to Ly, right. And similarly, on the right side of the box, when x equal to Lx, I am again changing the different y coordinates, and there what I am doing is basically I am going to decrease the temperature, right, if you remember. So, it is d float minus increment into Ly into temperature, which is the maximum temperature possible, 3.3, and as you increase I, right. As you increase I, the temperature is constantly decreasing along the y direction. This is at x equal to Lx. Now, in the other two, so when you change x, right, for y equal to 1 and y equal to Ly, which is the two ends of the box, right, like on the two ends of the box. So, you have to specify the temperature as you change x, and that is exactly what is being done here. Basically, I have already given the temperature, remember, at the corners in this loop. So, that is why this loop is from 2 to Lx minus 1, and I am suitably incrementing and decrementing decreasing the temperature at x equal to 1, that is the lower plate. I am increasing the temperature, and along at y equal to Ly, which is the top, at the top of the plate, I am decreasing the temperature, just as we discussed in the basically when we were discussing the schematics, right. So, this is what is I am setting the boundary conditions, right, and then I am saying okay, rest of the lattice I have set the temperature to be 0. I want to set the temperature to be 0, and I think that is set somewhere here. Well, one should give, yeah. So, I had set old temperature equal to 0 over the entire lattice here, boundary conditions, and then along the boundaries I specify the temperature. Now, I am storing, I have copied old temperature to temperature here, right, and I want to see what I have given as the initial conditions, right, and that I am storing basically in a file called initialize underscore 0 dot dat Ci equal to 0, if you see here, right. So, it is initialize 0 dot dat. So, I want to see what is the initial condition, and well, here I have set dx equal to 0.5 and dy equal to 0.5, but we are not going to use this because dx equal to dy. So, the final expression for the update of temperature does not have dx and dy, right, and the actual iterations to find the final temperature is being done here. So, after writing down the initial condition, basically initial condition before the start of the iterations, where everything is 0 except at the boundaries. So, here I am counting just like the previous class when we are doing a 1D loop. Here we are, there is a do loop here, right, with no specified number of iterations. This do loop ends here. Now, here we are going to scan each point in the lattice, leaving out the boundaries. So, j j goes from 2 to Ly minus 1, I goes as a dummy variable, I goes from 2 to Lx minus 1, and temperature at I j, at any particular I and j, or rather I and j j, is 1 by 4 into these temperatures, the previous temperatures at I minus 1, and here this is I plus 1, the two neighbors on plus x and minus x, and here on plus y and minus y, right, or vice versa. This is plus y and this is minus y. Note here I am doing it old temperature, because I am using the previous value of temperature, and when I equal to 2 say, right. So, I minus 1, so I is 2, so I minus 1 is 1, which means you are using the boundary temperature, right. So, to update, suppose I equal to 2 and j j equal to 2, you are going to use also the temperature of 1 2 and 2 1, which are at the boundaries, and those shall come from I plus 1, or rather I minus 1 and j j minus 1, right. So, we have in this step we have updated in one iteration the temperatures within the lattice within the blue line, if you remember what I showed towards the end of the lecture, right. And here I am checking for the tolerance. So, here basically I am going again from each lattice site except the boundaries 2 to L minus 1, 2 to L x plus 2 to L x minus 1, and if the temperature at each of these points, or rather the difference in temperature, the updated temperature is temp, the previous temperature is old temp for each value of J j and I I, if this difference is greater than a certain tolerance value 0.01, right. I set a dummy variable test equal to 1. This test at the beginning of each loop, this is just after the beginning of loop, is set equal to 0, and if the difference in temperature at any point along the lattice is greater than this tolerance value, you can set it to be 0.01 or 0.0001 10 to the minus 4, then test equal to 1. And only if the difference in temperature in one iteration for each of the lattice points is less than 0.01, then test will remain equal to 0, else test will be set to 1. If test equal to 0, exit the loop, this is the exit condition, right. And however, if you do not exit the loop, that means test has become equal to 1, then you set old temp equal to temp and redo this entire calculation, find out the new values of temperature for all the lattice points, right. Once you come out of the loop, you just want to know in how many iterations did you get your converged answer. The counter is set equal to 0 somewhere in the beginning of the code, and each time the code goes through this do loop, counter is incremented by 1, and you make the computer, the code, write down the value of the counter after you have come out of the loop. At the end, what do you want? You want to write down the value of the temperature at each of these lattice points, right, the value of temperature at each of these lattice points in a file. So, what I have chosen as the file is basically initialize underscore 1000 and CI equal to 1000 here, sorry 10,000 here. So, a file will be created, which is initialize underscore 1000 dot dat, and within that you are going to write down the temperature at each lattice site. So, this is there is a loop over there is a loop over I goes from 1 to Lx now, because you want the temperature also of the boundaries, and Jj equal to 1 to Ly, and for each value of II and Jj you are writing down the converged value of temperature. How are you going to visualize it? You can use it using MATLAB. What I have in this computer is Octave, which is basically an open source version of MATLAB. You do not have to buy Octave, you can just download it, and what I do is basically so I have already Octave installed in my computer, and so if I just type Octave, I will get a screen like this, right. And just to show you, to visualize this data, right. So, what do I have at the end? I have essentially, I will just compile it and show you. So, I have to basically G Fortran Laplace dot F90 minus O Laplace, then I run my code, right, and in 86 iterations it has converged, but of course, if you increase the tolerance to say decrease the tolerance to this value, right, then you can again compile, and if you run it, you need around 1068 So, 1068 iterations before you get the converged results of the temperature across the lattice, right, and the data is written, as I said, in initialize 1000.dat. So, these are basically 1 1 1 2 at each lattice point. The lattice goes. So, this is basically x coordinate, this is y coordinate decreasing from 1 to 34, and you write down the temperature. The temperature, as you know, you have set from 0.1, 0.2, 0.3, 0.4 up till at the boundary it is 3.4, and this is for x equal to 2. You have changing values of y or j if you like, jj if you like, for each value of x. So, basically for each value of x you are writing down all the values of y and the value of the temperature, the converged temperature. So, that is what you are writing down. So, that is what is there. Now, how do I visualize? So, I mean this is a huge file of line 1156 lines, 34 cross 34 I guess is 1156. Now, what do we do with this data? We want to know what is the temperature profile. So, we want to visualize the data in a xy lattice. To do that, I shall be using Octave, as I told you, right, and rather than write down my commands every time, I have written down the commands to visualize this data in a file called showcolor.m. The .m is important for running in MATLAB or in Octave. You must name your file which ends with .m, and all that I have done here is basically I have said load initialize 1000.dat, right, which means the software will upload the data to itself from the hard disk of this laptop, and then I have said okay, store whatever is there inside initialize.dat, save it in a array basically 1156 cross 3 times length array, and store it in a variable called data. I mean you are just naming that I am going to use data to store the data from here. Then so, all the data which is here has been stored here now. Now, you are saying that z. So, let there be a one dimensional array called z, and the third column and all the lines in the third column you store it in z. So, third column, if you remember, was the value of the temperature at each of these lattice points from 0 to 34 for each value of x and y. I am setting, so I am going to draw a color map. Okay, I am going to draw a color map, and the range of the color map will be from 0 to 3.5, and that is what I am setting in this command called c axis. Now, to plot, I have to tell Octave that for each value of x and y, the temperature should also be stored as a xy, I mean it should be stored in a square variable. Right now, from z equal to 3, it is stored in a linear, array, right, because that is how I wrote down the data when I wrote it down in the code, right, like x, y, temperature at x, y, and that currently is a linear array. To that I must convert it to a square array, so that when x and y is specified, the temperature is plotted, and that is being done here for do I equal to 1 comma 34, dd is some variable. So, basically 1 to 34th line, so basically dd 1 to 34 for a particular value of I stores the appropriate values from that long column. Just think about it, how am I storing it? I am saying from I minus 1 into 34 plus 1 to I into 34. So, 34 of my columns and I changes from 1 to 34 is being stored in this square array. This is a linear array of length 1156, and then I do p color. P color basically says plot. So, basically plot dd, which is now a square array here, and stores the value of the temperature for each x and y, x label x, x label y, and it is telling me the size of this array. Here you see that I have intentionally added an extra column and a row to dd given 35. This is basically to help me in visualization. Without much ado, let me show you how the color the temperature profile will look. So, this is your color bar, right, which says that blue is 0, and basically this deep red corresponds to temperature of 3.5, which I specified using c axis. Here, if you remember, the initial condition that we have given is it should increase from 3 to 3.4. Here the temperature was decreasing from 3.4 to 0, from 0 again it was increasing to 3.4. So, those are the boundary conditions, and we now solve the Laplacian iteratively, and now we have the temperature at each point within the lattice. So, basically if you want to know what is the temperature at this point, you have to just look, it is around 1.5 say, right, and if it is yellow, then you know that the temperature is around 2 or slightly more than 2, between around 2.3, and here you know that the temperatures are higher, and here the temperatures are cooler, because that is how we have set the boundary conditions. Now, suppose if we want to see the initial condition, right, so which is stored in a file called initialize 0 dot dat, right, and is basically this initialize 0 dot dat. Now, if I want to visualize that one, the initialize condition, so that is basically here I have to go and change the file name to initialize 0 dot dat, and if I want to visualize it, it is show color, and this was your initial condition. The temperature here was increasing, decreasing, here increasing, and here it was increasing, right, and this was this was your right at the beginning of the iteration. Everything inside the lattice except the boundaries had been set to 0, and after suitable evolution what we had was the data, the converged data is stored here, right, and if we just want to visualize that, this is what you have already seen before. This was your final temperature for the boundary conditions which are given. Now, suppose we had set the boundary conditions slightly differently, and suppose the boundary conditions, I have already tried that out, where suppose something like this. So, basically what I have here is both along x equal to 1 and at x equal to Lx, the temperature is increasing, right, and basically along Lx, the top part, you again you have the same temperature as previously. Basically what I have given here is old temperature 1, whatever is there on the x axis, it should keep on increasing, right. So, here I have changed the boundary condition from this line where it was as I specified before, where here I am saying it is the same as this, right. So, they are both increasing, and if you run this now, it converged in 1071 lines, and if I just use Octave, I have again saved the data in initialize 1000 dot dat. What you have is something like this, right. So, what I gave is basically the temperature increases from here to here, the temperature increases from here to here in the boundaries, but here I said let the temperature decrease and I forced it by the boundary conditions. Again here I said that let the temperature increase, right. So, I changed only this boundary condition, and for this would be the temperature profile, and you can read out what is the temperature at each of these points from this color bar, right. Now, if we had slightly more complicated boundary conditions, suppose that along this axis and along this axis I increase the temperature, but along this line and along this line I keep the temperature to be 0, right. And then what would be the temperature profile like? Let us have the look. We have to just change the boundary condition. I have already done that. Right. I have already done that, and all that I have changed basically here. If you see, so this is only the boundary condition changing here along at x equal to 1 for different values of y, I have increased the temperature. Along at x equal to Lx and for different values of y, I have again increased the temperature, increment of 0.1, but here from 2 to Lx minus 1, right, and for so 2 to Lx minus 1, different values of x at y equal to 1 and y equal to Ly, I have kept the temperature equal to 0, right. Now, if you run this code, and I have to also go here to a different directory, if you run this code, it has basically converged in 918 iterations, and well, let us see what the initial condition is, right. So, that you know, so this is the initial condition, and this is what I have given. All the temperature inside is 0, here it increases, here it increases. Along the boundaries, I have set them to be 0 and it shall remain 0. Along this and this, they shall remain 0, and after the solution of the Laplacian, if you iterate it and the result converges, the final temperature profile is going to be something like this, right. So, here you have high temperatures, suitably you have high temperatures here. This along this boundary I had mandated that the temperature should remain 0. Along this boundary I had mandated that the temperature should remain 0. So, here you have deep blue colors, right, and corresponding to so, I have put in the color bar now. So, the command to put in the color bar is just color bar and 0 to 3.5, and now you can see that here you have extremely cold temperatures, here you have warm temperatures, and the temperature basically goes in up till this point. Here it is again close to 0, but close to these regions with temperatures with very high boundaries, you have this profile. What is the message? You can put in whatever complex boundary conditions you want, fix up the temperature along the boundaries, and you can calculate the temperature within the plate, right. And I have given 3 different examples intentionally put to have different boundary conditions, and you can get the temperature profile. In the next class, we will discuss about some other kinds of boundary conditions. Thanks.